Hello friends, welcome back to this lecture series of earthquake resistant design of structures, where we are discussing the behavior of different types of structures and the effect of different shapes, layouts, and configurations on the performance of the structure under the earthquake forces. In the previous lecture, we have been discussing at length the architectural features and its effects on the building, and those discussions were limited to RCC structures. So today's discussion we are going to have regarding the masonry structures also, right? Because up to G+3, the buildings can be constructed in masonry also, or it can be a composition of RCC plus masonry both, right? So today's topic is going to be the discussion on the earthquake resistant design of masonry structures and the guidelines that the code is putting forward for construction of these type of structures, right? So when I look at the behavior of brick masonry walls, then the first thing that comes to mind is that the masonry itself, that is the brick itself, is a brittle material, right? In case of RCC, we see then RCC is a combination of concrete as well as steel. The concrete is a brittle material, but the ductility is introduced due to the use of steel, right? That is a reinforcing bar. Similarly, here in case of masonry structures, if you talk, then the structure is the basic material itself is brittle in nature, right? So as a result of these type of structures are going to be more vulnerable if not detailed properly and not designed properly for earthquake resistant design of structures, right? So masonry buildings are brittle structures and one of the most vulnerable of the entire building stocks under the strong earthquake shaking, right? So strong earthquake shaking, again, we have to keep in mind the design philosophy, and the design philosophy is such that it is minor, moderate, and strong, right? And in case of minor earthquake, it is suggested that the non-structural element should undergo failure. In case of the moderate earthquake, it is suggested that the structural elements are allowed to undergo failure, but they should be repairable in nature. In case of strong earthquake, it is suggested that structural elements may undergo irreparable damage, but in no case the structure should collapse, right? So our goal is going to ensure that these masonry buildings also stay strong under the strongest effect of earthquake, that is the third category, that is the strong. The large number of human fatalities in such constructions during the past earthquakes in India corroborates this. Thus, it is very important to improve the seismic behavior of masonry buildings. A number of earthquake-resistant features can be introduced to achieve this objective. And a couple of such features are going to be discussed in these 3 or 4 lectures that we are going to have on this particular topic. Now, first we understand how the forces travel, because in case of RCC, the things are pretty much clear that the force is concentrated at the floor level or the slab level, and then the beam column, the seismic forces are uh, concentrated at the beam column joints, and from the beam column joints, they travel from to the diaphragm action. They travel from one end of the building to the other end of the building, and then they come through the columns, and from the columns there is the foundation, and from the foundation to the soil below, right? But that is the case of RCC building. But what happens, or what kind of flow mechanics happens in case of masonry building, right? So ground vibrations during earthquake causes inertia forces at location of mass and movement. This is something which is an inherent property. Wherever mass is going to be there, the inertia force is going to be there, and this inertia force is going to be in the direction opposite to the application of horizontal forces. So these forces travel to the roof and walls to the foundation, right? So what the difference is going to be there? In case of RCC, it travels from the beam column joints through the diaphragm action to the other end of the building, and then to the columns, and then from the columns to the foundation, and then to the soil below. However, in case of masonry building, the flow is going to be from the roofs to the walls, and from walls to the soil, uh, uh, from roof to the walls, then to the foundation and to the soil below. The main emphasis is on ensuring that these forces reach the ground without causing major damage or collapse. Of the 3 components of a masonry building, that is roof, wall, and the foundation, the walls are the most vulnerable to damage caused by the horizontal forces and earth, right? Because these are the three elements through which the force is going to travel. So we have to make sure that all these 3 forces act in a proper manner so that the transfer of forces can be done easily. If any of these elements is going to be vulnerable in nature or not able to resist the forces that are going to be applied on it, then as a result of that, the entire system is likely to collapse, right? So the same thing that we have discussed in the previous slide is shown over here, right? That the force is going to travel from the roof to the walls to the foundation and then to the soil of the building. That is the basic components of the masonry building are shown in figure number A. Right now, what is going to happen is that there are two concepts. First is in plane bending and second is out of plane bending. Or in other terms, we can also say the weak direction and the strong direction as shown in the figure over here. Right. So what is going to be the weak direction and what is going to be the strong direction. Right. So in case if you talk about the wall, then if the force is applied along the length of the wall, right? If the force is applied along the length of the wall, then it is considered to be the force in the strong direction. Why? Because the stiffness of the wall in the along its length is going to be very huge. But if the same force is applied perpendicular to the wall, that is along the width of the wall, then it is considered to be the force is applied in the minor axis. The length is considered as major axis and the width is considered as minor axis, right? So when the force is going to be applied along the minor axis or the width of the wall, then in that case it is considered to be the force is applied in the weak direction. And same thing is said that, as I said, that in plane bending and out of plane bending, right? So when the force is going to be applied in the along the length of the building, then as a result of that, the bending is going to be in plane bending. But when the force is going to be applied perpendicular to the width of the building, the width of the wall, then it is going to be considered as out of plane bending. And in case of out of plane bending, it is going to be vulnerable. Why? Because what is going to happen is that it is the minor axis of the wall, that is the width of the wall. What is going to be the width of the wall? In case of load bearing structures or masonry structures, the maximum what we can say the width of the wall is going to be up to 450. It is 230, then 350, then 450, right? And then maximum 600. But those 600 thick walls were seen in the old era. In present era, we do not see that such kind of strong construction. So maximum width of the wall that we will see in today's time is 350, right? So 350 is going to be the width, that is going to be the minor axis. So what is going to happen is that when the force is going to act perpendicular, then what is going to happen is that the possibility is that the wall is likely to topple in the other direction. That is, it may collapse in the out of plane bending direction, right? So that is the same thing that is shown in the figure. And if the force is applied along the length of the building, then the length can be, let us say the length of the wall is 3 meters, 5 meters, 7 meters, then we can assume that the stiffness of the wall is going to be very much higher in that particular direction, and as a result of that, it is not going to cause much problem when the forces are going to be applied. So strong direction, weak direction. So major axis of the wall is strong direction, minor axis of the wall is weak direction, and out of plane bending is the most critical type of failure which is going to be there in case of masonry structures. That is, a wall topples down easily if pushed horizontally at the top in a direction perpendicular to its plane, that is the weak direction or the minor axis, but offers much greater resistance if pushed along its length, which is known as the strong axis or the major axis. Horizontal inertia force is developed at the roof transfers to the walls acting either in the weak or the strong direction. If all these walls are not tied together like a box, the walls loaded in their weak direction tend to top. Right? So, in order to understand this particular, what is happening is that we have seen the flow transfer, that the flow transfer is going to be from the roof to the walls and then to the foundation. Right? So what is going to happen, as I said, that all these three components, that is the roof, wall and the foundation, all need to act simultaneously and in a proper way. If either of these elements are not capable of resisting the forces, then the building is likely to collapse. Right? So same thing is shown in the figure number 1 over here, that once the force is applied to the roof level, then from the roof it is going to transfer to the walls. Now when it is going to be transferred to the walls, then what is going to happen is that if this force is going to be applied in the weak direction, then the possibility is that the walls may topple in the weak direction. That is the, as you can see in the figure, the walls in the shorter direction are likely to topple, right? And when the walls in the short direction will be toppling, then as a result of that, the entire structure is going to undergo major deformation, right? So this kind of failure is very much predominant in masonry structures or load bearing structures. Now, how do we avoid this type of failure? Then the simple answer to this question is that we need to ensure that the roof, walls, and the foundation, all these three elements act together like a box structure, right? How can this box structure or how this box effect can be developed? That is, the connection between the shorter walls and longer walls should be such that they remain intact when the horizontal forces are applied on this particular type of structure. So as you can see in figure number B, where the shorter wall, that is wall B, and long wall, that is wall A, both are interconnected with each other at corners, that is at right angles, right? So when this type of construction is done where the toothing is left on the either side and then these this two thing is being uh, done by means of RCC work, then as a result of that, the connection or the intermediate bonding between the two walls can be achieved, and as a result of that, it will act as a box effect when the horizontal forces are going to be applied. To ensure good seismic performance, all walls must be joined properly to the adjacent walls. In this way, the walls loaded in the weak direction get the advantage of the good lateral resistance offered by the walls loaded in the strong direction. Right. So, what is going to happen when everything is going to be in the box section? Then, whenever the force is going to be applied on the shorter walls, then they will get the support from the longer walls, and as a result of that, they will be able to resist the forces that are going to be applied. And then the forces can be further transferred to the foundation with much safety. Right. So, next the question comes is how to improve the behavior of masonry walls. So masonry walls are slender because of their small thickness compared to height and the length. That we all agree, because as I said, the thickness of the minimum thickness of the wall that we see in present era is 115 mm, and in regular construction we see that either the thickness is 230 mm maximum, or sometimes it may be 350 mm. So it is very much less as compared to its height and length, because the height of the wall is usually 3 meters, length depends on the plan. Right. So simple way of making these walls behave well during the earthquake is that proper connection should be there between these walls, and this proper connection can be established by forcing them to act like a box when they are subjected to horizontal forces. A number of construction aspects are required to ensure this box section, which we will be discussing in the subsequent lectures of this particular series for this particular topic. But just to brief you, firstly, the good interlocking of the masonry courses is required at the corners. Second, employing horizontal bands at certain height intervals. Then, that is height intervals, that is seal level, lintel level, roof level, right, gable end. These are different horizontal bands. And the third possibility is also the introduction of vertical reinforcing bars also at certain corners of the building, so that the interlocking is achieved between the walls in the two directions. Right. And the other aspect is that the size of the doors and the windows should be kept optimum, and also the location of the opening should be such that they do not make the walls big. We are going to discuss these couple of aspects in the what we can say the lectures to come. Thirdly, the tendency of a wall to topple when pushed in the weak direction can be reduced by limiting its length to thickness or height to thickness ratio. That is, the aspect ratio can be reduced. Right. So what can we do is that if you see that the length of the wall is too much, then we can introduce a cross wall in between, which will help us reduce the length of the wall in the other direction, in the weak direction, and as a result of that, it will also act as a support. And design code specify limits for this ratio, as IS 1905 and IS 4326 are giving us guidelines for the aspect ratios for several walls based on their thickness. A wall that is too tall or too long in comparison to its thickness is particularly vulnerable to shaking in the weak direction. Right. So same thing is shown over here in the figure, where the soil condition is shown and also the thickness of the wall is shown, and along with that the what we can say the effect is also shown, that is the short wall and the thick wall, both the things are shown. And same way here also it is shown that when the wall length of the wall will be too much, that is it will be too long, then also it is going to likely to veer in the weak direction, that is out of plane bending. So the wall of the length and should be kept in appropriate ratio with the thickness of the wall, and if necessary then cross wall should be introduced, which is shown in figure number B. And same thing happens in case of the height of the wall also, right, that the thickness of the wall is there, then accordingly the height should be there. If the thickness of the wall is less and the height is more, then also it is likely that the wall may likely to overturn or topple. So in order to reduce the height, because we cannot do what we can say, we cannot avoid the height, right? So whatever there is, in order to break the height, what we need to do is we need to introduce the horizontal bands in the building, which we are going to which we are going to discuss in the further lectures. Thank you for watching the video. Thank you.